All right. There we go. Okay, are we ready? So, just some introductions first. My name's Alex Bennée. I'm a virtualization and emulation tech lead at Linaro. So that means in my day job, I spend most of my time working on QEMU, although I have been known to delve into the KVM code from time to time. And I also do a bit of a side in VirtIO. So in today's talk, I'm going to talk a little bit about the history of instrumentation and specifically how that's been done with QEMU and some various downstream forks. I'm going to give a brief overview of the TCG plugin infrastructure, talk about some of the new features that have been added in the last year or so, and then have a little bit of speculation about potential future directions that we might want to move in. So let's start looking at some of the downstream forks. So QEMU is actually a quite heavily forked project. There are a lot of downstream forks, and a lot of them exist because people are just wanting to implement a machine model and they're not particularly interested in upstreaming it, or quite often there's quite a lot of academic work that's done on downstream forks of QEMU. But I want to talk about some that have turned into their own specific projects. So the first one I'm going to mention is Unicorn. So Unicorn is basically what libTCG would be. They've taken the TCG front ends and back ends from QEMU, librarized it, added a whole bunch of hooks, and then presented a whole bunch of language bindings. So the idea for that is to make it easy for a other project to take a CPU emulator, CPU-only emulator, and then build something around that. So there's lots of emulators that have been built off this, but the bit I'm interested in is the analysis tools. So it's quite heavily used for reverse engineering and doing malware analysis. So for example, if you're doing reverse engineering on a binary, you can take a block of code, feed it into the TCG CPU emulation and see how it behaves, and feed some data into it and see what happens. The next one I'm going to mention is the American Fuzzy Lopper. So this is a application fuzzer, and what application fuzzers do is they generate a corpus of data, feed it into a program, and then modulate that corpus of data and look at how that affects the execution of the program, see what extra branches are used in the space. And then you can basically improve the coverage of testing that you have for a given program. So this is actually a library, a whole bunch of different bits and pieces. They have a common library for building and managing these corpuses, and they have source and binary backends. So if you've got the source code for what you're building, you can push it through a compiler with the extra flags and then do it that way. But for binary, they have a QEMU-based backend, as well as actually a Unicorn-based backend for running these experiments. The final one I'm going to mention is a thing called Panda. So Panda is a whole system analysis tool. So again, it's a downstream fork of QEMU. They've added a whole bunch of additional stuff to it. So they have a LLVM code generator that runs alongside TCG. They do this thing called taint tracking, which is where you can look at a piece of memory that has a particular value that you're interested in, say, for example, a string, and then track where that data goes as it gets copied around the system. They also built their own record and replay and reverse debugging stuff. I think that was just because it wasn't as mature in the upstream at the time. And the big thing they do is OS introspection. So they've got a whole number of plugins that have an understanding of how operating systems work and are able to peek inside the operating system and extract useful information from what's going on. And they have a Python scripting interface on top of that, so you can do live experiments in a Python codebook and see what's happening. So why have these projects based themselves on QEMU? Well, we're basically victims of our own success. All of the major architectures that people are interested in, ARM, Power, S390X, RISC-V, Longsoon, they're all actively developed in QEMU. So we have one of the best multi-architecture simulators. Even x86 has seen some improvements in recent years in its emulation. We, as a project, generally focus on fidelity of execution. So it's important to us that when we emulate an instruction, it does what it really does on the real hardware. We don't try and take shortcuts just for just for performance reasons. But even given that, we're still relatively performant. We've had multi-threaded translation and execution for a number of years now. And importantly, we can run on a whole host of different architectures. There's backends for all of the major architectures, so you're not limited to a single host-guest combination. Obviously, there's downsides to having all these downstreams. Forking isn't a free activity. Generally, when you fork, you've got a smaller contributor pool. And if you're based on a project like QEMU, which is very actively developed, rebasing becomes a challenge. And these projects want to rebase because they want to get access to the newer features that we've done in the new architecture emulation that we're doing. But that becomes quite challenging. Another problem is you get multiple hook implementations. Each of these downstream forks has implemented their own hooks into the code to track what's going on. So obviously that's a whole bunch of duplicated effort. And also they tend to instrument at the architecture level. So they tend to put their instrumentation in specifically for the architectures they're interested in and not the other ones. Obviously, we don't code in the QEMU project caring too much about the downstream because the consumers of QEMU, we just want to provide the QEMU project. We're not doing it for the downstream's benefit. However, it does mean we're missing out on some nice functionality, especially the instrumentation. I find working on emulation a lot, especially when you're 2 billion instructions deep into an emulation looking for some failure in the emulation. Having a system like plugins is actually quite useful because you can write a little experiment to look for the condition you're looking for rather than hitting step instruction multiple times on the GDB stub. And obviously, having those developers working downstream means they're not working on the upstream. And although it doesn't happen that often, I have seen on numerous occasions fixes for particular models appear in downstream forks that have never got upstreamed. So from my point of view, anything we can do to encourage these developers to work more with the upstream is a good thing. So with that, let's talk a little bit about what TCG plugins are. So TCG plugins are a core feature. They're enabled by default, especially on 64-bit, and available for every TCG guest. So it doesn't matter if you're running RISC-V or MIPS or whatever, you can use the TCG the plugin functionality to instrument them. And it's a very lightweight system. It's zero cost when not used. So just to give a brief overview of the API, there's a number of events that you can subscribe to. The key one is translation. So every time a block is translated, you can subscribe to a translation event, and then you get an option to do some instrumentation. I'll talk about that on the next slide. There's a couple of other events. The vCPU idle and resume, basically whenever a vCPU goes to sleep and then comes back, you can subscribe to that. I'd be wary of using that for real performance analysis, because obviously under emulation, things will behave quite differently to how they would behave on real hardware. The init and exit hooks, again, are probably more useful for Linux user, so they also map to what happens when a thread is created and a thread is destroyed. And then for user mode, we also hook into the syscall layer, so you can hook whenever a syscall is made. So at translation time, you have a number of choices. You can either instrument the whole block. Just because a block is translated, it doesn't mean that all of the instructions in that block are going to be executed. But if you're just doing gross measurements of how the code behaves, you can put counters there. So we have two options. You can have an inline counter, and that's generated directly in the TCG code, and is the most efficient way to gather raw stats. Or you can generate a callback, in which case you can do whatever you want in the callback. And you can subscribe to every single instruction. And for every instruction, you have an option of adding inline operations, a callback, or a memory callback if you want to trace the memory operations. So there are some limitations on the plugin API. We don't give plugins free rein. We don't want them accessing the deep internals of the QEMU APIs. We give them a very specific interface to ask for information out of QEMU. And that's because translation is complex, and we don't want to push any of that complexity into the plugins. So specifically, we don't give them access to TCG IR at all. And some of the downstreams, for example, expose things like the translation block flush. That's not really something plugins should need to worry about. We should know when we need to flush all our translations and do it automatically. You can't change state, although I will talk about a point where we change state in a moment. And plugins are definitely not designed for simulating hardware. If you want to model hardware, the best way is still to write a device model for QEMU, get it upstream, and do it that way. Plugins are not intended as a way of bypassing your GPL obligations. We also don't provide all the information directly at the callbacks. We have a whole bunch of additional helpers. So you can fetch additional data on demand when you need it. So for example, for memory, we can get you the size of the memory operation, or you can extract the raw instruction opcode data, or find something like the nearest symbol if you're running in user mode. Disassemblers are also another good example. There's no point making plugins implement a disassembler for all the architectures when we already have disassemblers for all the architectures built into QEMU. So yeah, that's a feature we provide to them. So let's talk about some of the new features that have been added. So first of all, I'm not going to talk too much about reading registers because there's a talk right after this where they're going to talk about that more. Scoreboards, which is an enhancement of our inline operations. I'll talk about how we've expanded the memory APIs and then talk a little bit about controlling time. So scoreboards are our replacement for inline operations. So the problem with the original inline operations is they were inherently not thread safe. So if you have multiple threads of execution adding to the same counter, you could lose events. So if you're doing gross measurements of total number of events, it wasn't too much of a problem, but obviously it's not ideal. So now we've deprecated that mode of inline operation and everything is done through a scoreboard. So what a scoreboard is it's a chunk of memory that is dimensioned by the number of vCPUs in the system. And it's also dynamically resized by QEMU itself. So for example, if you're doing analysis on a Linux user program, every time a new thread is created, we'll bring everything to a safe stop, expand the size of the scoreboard, and then start stuff up again. So the plugin doesn't need to worry about doing the management of the memory for that. And what a scoreboard allows you to do is every time you do an inline operation, it's indexed by the vCPU. So it's inherently thread safe because every vCPU has its own set of counters. And then we provide some helpers so you can sum up the counters across all the vCPUs. We've added a new inline operation called store U64. So instead of being able to just add to a counter, you can store an absolute value. And this is useful for doing other types of tests. So you can store the program counter at particular key points or store other information that you want to check at the next block. And finally, we've added conditional callbacks. And conditional callbacks allow you to push more of your plugin down into counters and then only take the cost of a callback when you reach a particular condition. So you can have a decrementing counter and only call the callback when you've had a certain number of events. So the memory APIs, we've now got two. So we've expanded the original memory API to allow you to get the value that was loaded and stored. So we originally didn't implement that just because we were a little concerned about people using that to run around the GPL, but I think that is less of a concern now. And this is the precise way. So if you're interested in every single memory operation and precisely capturing what a particular instruction does, you should use the original memory API to do that. But that can get expensive, because if you're instrumenting every single instruction for every single memory access, that's going to add up to your execution time. So there is a second memory call called read memory virtual address, which allows you to read a chunk of the virtual address space into a buffer. And this is really to be used when you know that the memory you're looking at is unlikely to change. So the key example is when you're about to do a system call, you know all the variables should have been set up, and then you can read the values of those variables out. Controlling time. So one of the things about running an emulation in QEMU is we generally present host time to the guest. And this has a couple of effects. It means if you're emulating a microcontroller, your microcontroller has way, way better performance under emulation than you'd expect it on a real device. And conversely, if you're emulating a big system with lots of application processors, the cost of emulation will eventually show up as the inefficiency of the emulated cores only getting a certain rate of instructions through. So the solution for this in the upstream QEMU is to use a thing called iCount. So iCount is an instruction counting framework, and that allows us to present a virtual time to guess based on the number of instructions we've executed. But iCount is explicitly a single-threaded mode of operation. So I'm sorry, the diagram's a little bit dark here, but what I'm trying to show here is the round-robin scheduling we do. And what happens is we start at the top, we allocate a block of time. Usually it's the number of cycles before the next timer event is going to fire. We divide it by the number of vCPUs, and then execute each vCPU in turn. Now, each vCPU doesn't necessarily use up its full allocation, so at the end of its execution, we have to work out how many instructions it executed, and then update the system time, and then present that. So that's available to the guest. And this means that you get some interesting patterns because you're actually running each vCPU sequentially rather than in parallel. So with plugins, we've added a new API that allows plugins to control system time. So only one plugin can do this, but it can request from QEMU to become the sole arbiter of time. And then all the logic that decides how much time has passed can be pushed into a plugin. This is going to be useful for people that want to do sort of like complex modeling, time modeling of their CPU, where we have absolutely no interest in putting that complexity in the core QEMU code. But you can do that in using the plugin system. So this is inherently multi-threaded. We have an example called the instructions per second plugin, and then that runs all the vCPUs in parallel using multi-threaded TCG. And then as each vCPU gets to a particular point, it either updates the time if time has moved forward, or if it finds that it's run too far, then that thread will sleep whilst it gives time for the other vCPUs to catch up. So this is the first example of plugins being able to modify state for the guest. Just mentioned that you can find other examples of uses of plugins in the contrib directory. So a couple that have come in recent months. The BBV is a basic block vector generator. So this is just generating execution profiles based on basic blocks that can be consumed by some external tools. So there's a tool called SymPoint, for example, that understands these files. Stop trigger is just a very simple plugin that allows you to exit QEMU when you either hit a total number of instructions executed or if you hit a particular address. And that's just useful for running experiments. So say you want to see if a particular instruction ever gets executed, you can mark that in the stop trigger plugin and then give it a corpus of data. And if it exits with your exit code, good. If it doesn't, then obviously that wasn't the change you wanted to make. And then CFlow is a more sort of detailed control flow analysis tool. So you can identify hot branches and where all the heavy return points are in your code. So let's just talk about some potential future improvements. So these aren't ideas that are necessarily going to go in, but some areas that we might want to think about. So the first is, how can we do things on a more semantic basis? So for things like fuzzers, where allocation of memory is important, we need to know things like where is the malloc and where is the free in the code. So we already provide a basic method of getting the symbol information for a given address, but that doesn't tell you enough detail to be able to identify the start of malloc and the start of free. So maybe we want to consider some sort of hypercall. So Valgrind, for example, does this. It adds a little bit of minimal instrumentation to the important libraries. It emits a special sequence of instructions that can then tell the Valgrind core, this is a memory operation and this is the address that you're using. And another thing that we might want to consider for this is having inter-plugin communication. So this is one thing that Panda does, is it has lots of plugins that understand lots of different things, and those plugins can provide services to other plugins, so you don't have to re-implement the logic in your particular experiment. You can just use a constellation of plugins, each concentrating on its own thing. And there were actually RFC patches posted for this a while ago. We didn't merge them because we didn't have a use for them at the moment, but if we start seeing more useful plugins, then maybe that's something we want to consider. We've already got 2 memory APIs, so obviously we might want to add a third. So we have a fast and racy one that can just read bits of memory, and we have the slow and precise one that can instrument everything. But we do actually have the option to do range-based stuff, because QEMU obviously marks out areas of memory for hardware, and we could use the slow path mechanism to be a little bit more efficient and maybe present a range API to the plugin so it could say, this is the range of addresses I'm interested in. Another thing we might want to think about is alternative bindings. At the moment, all plugins are written in C, and obviously we know the problems that can come from writing stuff in C. There's been some interesting downstream examples where people have wrapped a Rust API around the plugins interface, so you can write your plugins in Rust. Whether or not we want to officially support different language bindings for plugins in the upstream, I think is something we want to think carefully about, because that might require us to be a little bit more formal about specifying a proper API. And at the moment, things are moving quite a bit. Finally, and just to summarize, so we now have a core plugin API available in QEMU. There is some interest from the downstream forks of migrating their hooking code to use the core API. I don't think this is going to replace the need for downstream forks. Downstream forks will always want to have the freedom to do their specific thing, but maybe we can reduce the delta, and hopefully that will be beneficial to everyone, both the downstreams and the upstreams. So with that, I think I'm close to time. Do we have any questions?
Several years ago, I was doing the Valgrind port for S390, and some of these plugins thing actually reminded me of Valgrind. And I'm asking myself if we could go much further with that plugin and scheme to do something similar like Valgrind has, where you basically have the intermediate representation in Valgrind, where you can then add instrumentation on top. Would that be powerful enough to go down that path, or is this a completely different set of use cases that you're addressing here?
No, absolutely. I think the Valgrind use case is an interesting one. So I can only speak from my experience with ARM. So obviously the ARM architecture has seen quite a lot of changes over time, and Valgrind has struggled to keep up with the newer architectural updates. But obviously we have a much more complete emulation of the CPU. So what happened with Valgrind is they've got their instrumentation layer, but they also have their sanitizer libraries. And those sanitizer libraries have become libraries in their own right, and now they're used by things like the GCC and LLVM sanitizer plugins. So yes, if we could work out what extra bits of information we need to get out of plugins, we could just then link into the existing sanitizer libraries and then do sanitizer runs using QEMU as a backend for it. And absolutely, that's something I'd like to be able to do.
Have you seen any attempts at abusing the plugin interface for things it's clearly not intended to do?
No, not so far, but I suspect if there are attempts to abuse the plugin interface, they're probably hidden away in private forks inside companies, in which case it's not actually a GPL problem, because as long as they don't distribute it, they can do whatever they want with their downstream. And we already know there are internal downstream forks of QEMU in a lot of the CPU manufacturers, which they use for their modeling. It would be nice if we could encourage them to upstream some of the more useful bits, though.
Okay, so you've talked about plugins inside QEMU. What about using QEMU itself as a plugin in different projects? Like if you want to understand some particular piece of binary code, then you might want to write some unit tests against it or something. And I think QEMU is being used for that.
Yeah, so I mean, I alluded to this when I was talking about Unicorn. One of the problems Unicorn has had is keeping up to date with our CPU emulation because it's a relatively small project compared to QEMU. I think the cleanup to allow us to build the TCG front ends and back ends cleanly in the upstream project is something that we're actively looking at for doing heterogeneous modeling and stuff like that. And maybe one of the outputs of that could be an officially libradized version of libTCG. But I guess we have to ask ourselves as a project of, do we want to have the maintenance burden of maintaining a stable API for external consumption versus just having a cleaner internal implementation that makes it easier to build QEMU itself? Because obviously when you provide a library, you then now need to think about library stability and how often you change the API for it.
And do you? I mean,
well, for the plugins API, we've explicitly said we're free to change the API whenever we feel, and the best way to make sure your plugin doesn't break is to get it upstreamed into contributions.
But we could just say it's unstable at the moment until we figure it out, right?
Yeah, we could. I suspect we need a few more cycles of it as an internal API before we might want to make it a properly published API. But. Anyone else?
And what about big endian support? I've seen some to-do comments in the plugins where it says, for example, at the register, when you dump the register contents, is this an issue right now in the API, or could it just be implemented?
So we know the big endian mode of loads and stores, so you can query that. And in fact, the latest memory plugin API updates have a system test that work on both big and little endian systems. In terms of the register values, I think you just get the registers in host endian format, which if you're just looking at the value of it should be fine because you'll want it in the host endian format for the plugin itself.
Well, unless you dump it, then it's always in host format or order.
Yeah, so I think the execlog plugin tries to make sure that stuff is dumped in the right order, but we've got the information, so it's just a case of cleaning up the plugins to do it. All right, any more questions?
Just some clarification for the last question. Well, the register API actually uses the guest endian, and that is because it is derived from GDB stub API, and GDB stub API is independent from the host endian, so it just uses guest endian.
Oh, okay, yeah, so it's the other way around. We have to translate from guest to host when we dump the value of the register. That's right. All right. Thank you all very much. You can find me on my socials there, and thank you.